I wanted to look at this problem just because it's a fun problem. The law of Laplace states that the tension in the wall of an artery is equal to the pressure times the radius of the artery. And so this relates tension in arterial wall to the pressure, and Hooke's law, which if you remember Hooke's law is the same, you may remember it from springs, where force equals kx, right? So we have something here that's similar. Tension is k onto r minus r naught. R naught is the nominal radius of the artery under zero pressure. So we want to derive an expression for r as a function of p, right? So what do we know? We know T equals PR, and we know T equals K onto R minus R naught. All right, so we have this. We can rearrange this. We've got PR minus KR is minus KR naught. I'm going to consolidate some, multiply through by a minus sign. K minus P is KR naught. All right, great. K minus P is KR naught, and so R is KR naught divided by K minus P. Now we have an expression for R as a function of P, and you can see in question B, is there an infinity in this? And there is, right? When P equals K, the denominator here goes to 0, and the radius blows out to infinity. What does that mean? That means your artery bursts. All right, well, let's plot R versus P. All right, R versus P. Let's go over here. P and R. Let's put in some values for K. K, I'm going to put in K as 250 torr, or 250 millimeters of mercury. I'm going to put in R naught as 1 centimeter, which is roughly the radius of the aorta. And let's take, there's no reason to go too low here, 45, 50, right? Okay. Let's take this down to around, we don't need to go all the way to 250 because that's where it blows up. All right, so what's the radius? The radius is K times R divided by K minus P. Now, some of these need to be constant. Put my dollar signs in. Okay, so you can see here that, and I'll plot these. Insert, scatter plot. All right, so here's R, here's P. You can see that despite the fact 250 is a infinity, well before that you're in trouble, right? Well before that you're in trouble. And so that's not pretty, right? And now they also said let's plot T versus P. Well, if we know P and R, we know T, right? So let's go over here and put in T. T is just the product. All right, so you can see here, I could add to this, or I'll just do another plot. Let me copy this. Okay, and I'm just gonna grab that, move it over. There we go. Now we T versus P. All right, both of course have issues as this goes to infinity. Not a great thing. Okay, so how does the body actually deal with this? Well, arteries, which would be unstable, right? I mean, these things would help. Pardon my language. Let me go back to this. The last time I inadvertently went unmedicated for my hypertension. My systolic hit 220, right? So um, if arteries actually behaved exactly like this, I wouldn't be here making this video right now. Okay, so let's go back to step C, or part C in this, right? Arteries would be unstable if they balloon out, right? Okay. So what happens is they actually get more stiff. So K is actually CR, where C is a stiffness, right? So basically, as the radius increases, the stiffness of the artery increases. So if I put in K as CR, I'm just going to start here again, copy that down here, and we're going to change K to CR. Okay, so first you can see this R and that R divide out, right? And now I've got P equals C onto R minus R naught. And if I solve for R as a function of P, it's going to simply be P over C minus plus R naught, right? P over C plus R naught. And now we're in a completely different situation, right? Depending on what this stiffness constant is, um, we avoid aneurysms on a much more regular basis. All right, that's it for this little example problem. Hope you enjoyed it.